Hi, my name's Ethan. I'm doing Module 13 on biodiesels. In this video, I'm going to go over how vegetable oil can be turned into biodiesels through the process of transesterification. So to start off, I'm going to go over a couple important definitions. So a nucleophile are molecules that donate their electrons in reactions. So they're going to have high electron density. And electrophiles are molecules that accept the electrons in reaction. And these usually have low electron density. So functional groups are sites on molecules with either high or low electron density. So these are where reactions occurred. So next we're going to go a little bit more in depth on nucleophiles. So what makes a good nucleophile? First off, the greater the negative charge, the more likely an atom is to give up an electron pair. Next, the less electronegative an atom is, the stronger the nucleophile. And this is because electronegative elements pull electron density towards them. So next, nucleophilicity is going to decrease with increasing steric bulk. So the bulkier a molecule is, the less likely that molecule is to act as a nucleophile. And finally, pi bonds can also act as nucleophiles. So some quick examples of strong nucleophiles include bisulfate ions, iodine ions, bromine ions, and cyanide, which is pictured on the slide. So now we're going to talk about electrophiles. So what makes a good electrophile? So atoms with higher electronegativity are now going to make better electrophiles for the same reason that electronegative elements are going to pull electron density towards themselves. Electron deficient atoms are likely to be electrophiles. And with increasing steric bulk, electrophilicity is going to decrease. So in general, the bulkier a molecule is, the less reactive it's going to be. And finally, alkyl halides make great electrophiles. And some examples of these are iodoethane, 2-chloropropane, and 1-bromo-2-methylpropane. So some other examples of strong electrophiles include borane, hydronium ions, and halogen molecules. So fluorine, chlorine, bromine, and iodine. Okay, so I'm going to go over the history of biodiesel fuel. So Rudolf Diesel developed the first diesel engine in the 1890s, although his engine could only run on vegetable and peanut oil. This wasn't great because vegetable oil is too viscous to effectively be used as a fuel. So in 1937, G. Chauvin was granted a Belgian patent for the transesterification of vegetable oil to biodiesel. So biodiesel is a much better fuel than vegetable oil. And the first biodiesel manufacturing plant was started in 1985 in Austria, and since then, it's manufactured worldwide. Next, we're going to look at the chemical structure of triglycerides, which are the main component in vegetable oil. So triglycerides contain a glycerol backbone with 3 long-chain carboxylic acids connected through ester chemical bonds. So in the case of vegetable oil, we have palmitic acid, oleic acid, and alpha-linolenic acid. So these carboxylic acid chains can contain carbon double bonds, and these carbon double bonds affect the melting temperature of the triglyceride. All right, so now we're going to look at some of the properties of triglycerides. So triglycerides have long-chain hydrocarbons, so it's going to be a large branch molecule. These triglycerides are also neutral and nonpolar. So this means that these molecules are going to have high viscosity caused by internal friction between these long hydrocarbon chains, and they're also going to be hydrophobic, meaning they're not going to be soluble in water. So now we're going to look at a general overview of transesterification. And so in transesterification, triglycerides are going to react with an alcohol to form alkyl esters and a glycerol. So in this reaction, strong acid or strong base is going to be used as a catalyst. So on the slide, you can see the reaction drawn out, and you can also see that this reaction is in equilibrium. So now let's look at some of the properties of the alkyl esters that are going to be produced in the transesterification reaction. So these alkyl esters are still going to be large branch molecules, but now they're going to exhibit some weak polarity. So they're going to have lower viscosity, and they're going to have, due to the weak polarity, they're going to have some solubility in water. So what's the point in turning vegetable oil into biodiesel? Well, the triglycerides in vegetable oil are far too viscous to be effectively used as fuels. And the alkyl esters produced in the after transesterification are far less viscous than the triglycerides, making them better fuels. So fuels can't be too viscous, as they can cause some problems for engines, such as increased metal-metal contact, increased oil consumption, leaking seals, and increased fluid friction, which reduces your fuel economy. Okay, so now we're going to look at the reaction mechanism under basic conditions first. So, in this first step, the alcohol is going to be deprotonated by the base, resulting in the formation of an alkoxide ion. So this alkoxide ion is going to bond with the carbon in the center, and at the same time, the double bond between the oxygen and the center carbon is going to break, and the negative charge is going to be transferred to the oxygen. And this is illustrated by the two arrows in the image. In this next step, first, the R prime group of our initial ester is going to act as the leaving group and is going to be removed from the intermediate. The oxygen is going to retain the bond pair of electrons, and this is going to result in the formation of a new alkoxide. And finally, the double bond between the center carbon and the oxygen is going to be reformed. And that is the reaction under basic conditions. Now we're going to look at the reaction mechanism of transesterification under acidic conditions. So all that's going to be happening in this first step is the carbonyl oxygen is going to be protonated by the acid. So next, the presence of two lone pairs on the oxygen of the alcohol is going to make it into a nucleophile. So that means this oxygen is going to give its two electrons to the carbon, and at the same time, the double bonded oxygen is going to break its bond and take those electrons. And this is going to result in the formation of a new intermediate, shown in the picture down below. So next in this reaction, an intramolecular proton transfer is going to occur in the intermediate. So the positive charge is going to be moved from the oxygen of the alcohol to the oxygen of the ester, and this is shown down below in the picture. So these two molecules in the picture are actually the same, and these are known as resonant structures. So in the next step in our reaction, our protonated oxygen is going to act as our leaving group, so that carbon-oxygen bond is going to break, and the oxygen is going to retain those electrons. And at the same time that happens, the carbon-oxygen double bond is going to reform. So that's illustrated by the arrows in the image down below. So in the last step of this reaction, the positively charged oxygen on the ester is going to be deprotonated, and this is going to give us our biodiesel, and it's going to regenerate the acid that we used at the beginning of the reaction. So that's the reaction mechanism in acidic conditions. Next, we're going to be looking at what's driving the reaction. So first of all, alcohol is going to be constantly added to keep the reaction favoring the products. So for about every mole of triglyceride, we're going to be using about 6 moles of alcohol. And that's going to keep the reaction favoring the products. And this reaction is also relies on the acid or base catalyst as well. So next, we're going to look at some of the other applications that transesterification is used for, because it's not only used to make biodiesels. So first is the synthesis of polyester. So the synthesis of polyester is the largest scale application of transesterification. So diesters and diols are going to undergo transesterification to obtain macromolecules. Another thing transesterification is used for is it plays a role in fat processing. And finally, the glycerol that's going to be produced in the reaction is used in skincare products such as soap. So finally, we're going to look at the impact of using biodiesel on the environment. So biodiesel is both non-toxic and it's biodegradable. And the combustion of biodiesel is going to produce far fewer air pollutants than other fuels. So all in all, one of the biggest benefits to using biodiesel is it's really good for the environment. And finally, here are my references, and thanks for watching.